In this video, we're going to analyze the concept of chemical equilibrium. So when we talk about chemical reactions in grade 11 and before this unit, you were essentially used to seeing chemical reactions that sort of looked like this. So you had, let's say, your reactants. I'm not going to put in the states, but your reactants, they react and they produce, you have an arrow there, let's say some sodium chloride. And you were used to thinking that reactions essentially just went in one direction. So from left to right, from reactants to products. But in reality, that's not the case. Chemical reactions can actually go both ways. So essentially what happens is your reactants will produce product, and as your product is being made, a chemical reaction could go in the reverse. The product will react and reform the reactants. And so the idea is that a system will essentially reach this point where you'll have reactions happening that go left to right and right to left at the same rate. And that's what we call equilibrium. So we're going to come back and study the different types of equilibrium systems in just a minute. Let's go take a look at what equilibrium means, and then we'll come back and take a look at these examples over here, the three types of equilibrium systems that can occur. The plural of equilibrium is equilibria. If you were saying plural, rather than equilibriums, you say equilibria. So here we have a chemical reaction. We have A plus 2B produces 3C and 4D. The blue arrow shows the forward reaction. So going from left to right is forward. Going this way is the forward reaction. And then the red arrow shows the reverse reaction. So going from right to left is the reverse reaction. And so you'll notice that because the reaction can go both ways, left to right, right to left, we have a double arrow to represent that. Sometimes we'll have the half double arrows like this instead, rather than the full arrows, but it's the same idea. So there will be a point where this system will reach what's called equilibrium. And at equilibrium, what happens is the rate of the forward reaction, so going left to right, is going to be equal to the rate of the reverse reaction. So the reverse reaction is going to be going right to left. So at that point, you've reached equilibrium, when the rates of the left to right is equal to the rate of the right to left reaction. And that's called an equilibrium, a state of equilibrium, and systems will eventually reach that as long as they're closed systems. So if you have a closed system where nothing can basically disturb the system, you don't have anything coming in, leaving, you just let the system do its thing, it's going to try to go towards equilibrium. So let's take a look at what this can tell us. So we have, these are the rates. This is the rate of the forward, and this is the rate of the reverse. And at equilibrium, they're equal to each other. Let's take a look at what that looks like graphically. So initially, when we do a reaction, we might only start off with reactants for the forward reaction. So we'd have a lot of reactants, and we have no products at the beginning because a reaction didn't happen. Now, over time, what's going to happen is the reactants are going to be used up. And so essentially, you start off with a very high rate of the forward reaction. But as your reactants are used up, well, now the forward reaction rate starts to decrease a little bit progressively because you're using up those reactants. And at the same time, as you're using up the reactants, you're producing product. And so now the rate of the reverse reaction going from products to reactants is increasing. And eventually there'll be a point where the rates will meet and they'll be equal. So at that point where the rates of the reverse and the forward are now equal, you have now reached what's called chemical equilibrium, where they're equal to each other. So mathematically, you could represent it as seen here. So here we have the forward reaction rate equal to the reverse reaction rate. And essentially what you can do is you can create a ratio to isolate for the rate law constants here. And so if you essentially send the rate law constant to the other side, that becomes a division. And if you send these reactants to the other side, that also becomes a division. So we've created a ratio. We have products on top and reactant concentrations at the bottom. And so now this ratio of the forward K and the reverse K is an integrated K. It's a ratio. It includes both the reverse rate constant and the forward rate constant, and we give this mu k value something called an equilibrium constant. So this is called an equilibrium law constant, or just equilibrium constant. And this whole expression that we've created here, this is called an equilibrium expression or equilibrium law expression. And so basically the idea is that if I have concentrations for a reaction, I can plug them into this equilibrium law expression and see if they've reached equilibrium. If they equal a certain k value, I can say based on this k value, my system has reached equilibrium. And so mathematically, you can now figure out if you've reached equilibrium or not. And if you haven't, you can figure out what needs to be done, or which way the reaction needs to go in order to reach that equilibrium. So the general idea I need you to understand about equilibrium is that when you have a chemical system that is at equilibrium, you're going to have a constant ratio between the concentrations of the products and the reactants. In other words, because the rate of the forward and the reverse are now equal to each other, the ratio that we create here between product and reactant will always be the same. So as you produce reactant at the same rate, as you produce product at the same rate, you're going to go backwards and produce reactant. So it looks like nothing's happening anymore. There's still reactions happening. It just looks like nothing is changing anymore. Only because at the same rate that you're producing product, you're destroying it to make the reactant again. Think of it like if you're on a bus, a city bus, for example, and there's people on the bus. Let's say one person gets off the bus and one person gets on. At the same rate, it looked like nothing changed. It looked like there was no change happening because one person got off, one person got on at the exact same rate. So it looks like nothing changed, even though people did move. So we often like to call that a dynamic equilibrium, And so that ratio, that constant ratio that exists between the concentrations of products and reactants, that really is essentially your equilibrium constant. That's what that is. So that equilibrium constant is the constant ratio that exists between the product and the reactants at equilibrium. And so this is our equilibrium expression over here that we can use to determine if a system's at equilibrium. So the way you do it is you do your concentration of your products multiplied by each other, and these concentrations must be raised to the power of the coefficients of the products. And then you also have then you're going to do divided by the concentration of the reactants multiplied by each other, raised to the power of their coefficients. And so that will give you your equilibrium constant, and that will lead to an expression that allows you to figure out if you have equilibrium or not at that point. So one more important point to mention about the K value, the equilibrium constant here, is that it's important to state what temperature you're reporting this K value at when you're doing problems. And that's because the K value is temperature dependent, right? Rates of reactions are affected by temperature. And so, your forward and your reverse are affected differently by the temperature because one might be exothermic, one might be endothermic. Because rates are affected by temperature, your K value will be affected by temperature as well. So it is important to conduct your experiments at constant temperatures, or to state what temperature you're doing an experiment at, so that way we can have a nice control and a nice easy understanding of our equilibrium system at that point. So here we just saw essentially what equilibrium means, and that most reactions will reach equilibrium at some point. They start off by having a very high rate of the forward reaction and a very low rate of the reverse, because there's no product there at all to begin with. And eventually the reverse increases as the forward decreases, and they reach a point where they have equal concentrations. It's not equal concentrations, sorry, that's bad to say. Do not say equal concentrations. We'll see that in the next video, where they have equal rates of reactions, not necessarily concentrations. And at that point where they have equal rates of reactions, they're said to be at equilibrium, and we can develop an equilibrium expression in order to illustrate that or see if we are at equilibrium. So in the next video, we're going to take a look at how to write equilibrium expressions for different systems. And then we're also going to take a quick look at the 3 different types of equilibria that exist, or the main ones that we study in grade 12.